Welcome to MSP lecture series on main group chemistry. In my last lecture I was discussing about group 13 halides. Let me continue from where I had stopped. I was discussing about trihalides of boron as well as aluminum. So, let us look into other 3 elements in the series. Gallium and indium trichlorides and tribromides also form adducts very similar to aluminum as well as boron halides, but with coordination numbers greater than 3. So, here one can anticipate coordination numbers of 4, 5 or 6. For example, MCl6 3 minus or MPr6 3 minus MCl5 2 minus MCl4 minus and also MBr4 minus. So, these are the possibilities where M is essentially gallium or indium. And also one can also form simple adducts of this type. For example, X3 gallium L is L is a Lewis base and also X3 indium L. So, they are essentially neutral Lewis bases such as trimethylamine or ether. Thallium trihalides are less stable than those of the earlier group 13 elements. In fact, thallium trichloride and thallium tribromide are unstable with respect to conversion to the corresponding monohalides. So, that means in fact, when you make thallium trichloride or thallium tribromide, they are oxidizing in nature. Here one can anticipate this kind of reaction. So, the compound thallium triiodide is isomorphous with alkali metal triiodides and it is really a thallium 1 triiodide. So, sometimes people get confused with this formulation indicating that the thallium is in +3 state. It is not so. Still thallium is in +1 state and its I3 represents here I3 minus. So, that one can conveniently write this one as a plus and I minus. This is the correct representation of thallium iodide, triiodide. And when thallium triiodide is treated with excess of iodine, an interesting redox reaction occurs with the formation of tetraiodide of this type. And thallium 3 also exhibits coordination numbers higher than 4. I had already mentioned in complex chlorides prepared by the addition of chloride to TiCl3. For example, one can also see thallium having this kind of geometry. This is thallium 2 minus, or it can also have an octahedral geometry in this fashion where we have 3 bridging chlorides. So, this is essentially thallium 2, you have 9 Cl9 and then it is 3 plus 3, 3 minus. Okay. So, all the halides, that is trihalides, are powerful Lewis acids and they readily form MX3L. Often BF3 used as an adduct of diethyl ether. The formation of anions such as MX4 minus from MX3 by addition of halides can also be viewed as Lewis acid base complex formation. For example, if we say LiF and if you add BF3, it essentially it forms LiBF4 and this is also essentially formation of a Lewis acid Lewis base complex. And for aluminum and other heavier group members, more than one ligand is able to be added up to a maximum of 6 coordination that you saw. Okay. And when we come to the lower oxygen states, all group 13 elements do form diatomic halides. However, except thallium, all are unstable towards disproportionation to the metal and the trivalent halides. Even gaseous thallium chloride is unstable to disproportionation. So, aluminum Cl and gallium chloride monochloride can be formed by the reaction of aluminum or gallium metal with HCl at high temperatures and low pressure, that essentially gives red this one aluminum chloride or gallium chloride, which are condensed at low temperature, that is at 77 Kelvin. One can think of on warming, what would happen is they undergo disproportionation to give the corresponding MCl3 plus 2M. This is a typical disproportionation reaction. Okay. And in case of boron, one can start from BCl3 and treat this one with mercury. It forms B2Cl4 plus HgCl2. Okay. Or one can take 2 BCl3 and treat with copper atom to generate B2Cl4 through the formation of 2 equivalents of cuprous chloride. So, some atoms of the same element are oxidized and others reduced in the same reaction is called as disproportionation reaction. Disproportionation reaction is nothing but a reaction in which the same element is oxidized as well as reduced. And of course, B2Cl4 decomposes at room temperature to form progressively higher analogues such as can give B8Cl8 or B9Cl9 and also large clusters such as B10Cl10 or B11Cl11 or even B12C12. Okay. And gallium 2 occurs in the species Ga2x6 2 minus. So, where X equals chlorine, bromine or iodine. Okay. And essentially this is formed by the electrolysis of gallium metal in strong acid. So, these essentially contain a gallium to gallium bond. As a result, this accounts for +2 oxygen state, but are readily oxidized by halogens to give GaX4 minus species. Okay. Okay. Now, let us look into the compounds of boron with nitrogen. So, that is a popular well known compound series that is called boron nitrates. Okay. So, boron nitrate consists of planar sheets of atoms very similar to the graphite. Boron nitrate is a white crystalline solid, resembles graphite in its structure. A boron atom bonded together with a nitrogen atom that has 8 valence electron. So, for example, 8 valence electrons are coming, 3 from boron and 5 from nitrogen. So, that will make 8 electrons, and similarly in case of 2 adjacent carbons, if we take, we have a total of 8 electrons, S2p2, S2p2. So, that we have 8 electrons, and similarly in case of boron nitrate also, B and N accounts for a total of 8 electrons. Okay. So, this is how the boron nitrate layer structure looks like, and we have alternate double bonds, and this is very similar to the graphite. And how to prepare these boron nitrates? One can conveniently prepare starting from boron oxide and its interaction with ammonia at high temperature. So, let me write down few reactions that are available to make boron nitrate. B2O3 plus 2NH3 at 900 degree centigrade, at 900 degree centigrade. Okay. Since the ratio is 1:1, they are essentially written as Bn, or one can also write BnN. One can also prepare starting from boric acid. Of course, at same temperature 900 degree centigrade can give Bn plus 3H2O. One can also treat B2O3 with urea, but at 1000 degree centigrade. The common form of boron nitrate has an ordered layer structure that I showed you in the previous slide, containing hexagonal rings with alternate boron and nitrogen atoms, and boron Bn bonds are shorter than in adducts such as trimethyl amine BBr3 or others. So, the Bn bonds in boron nitrates are shorter than those observed in adducts such as So, this distance is shorter than this one, this distance is longer than this one. So, in boron nitrates Bn bonds are shorter. Okay. So, you can see in this slide the layers of graphite, and essentially the layers of graphites are separated by a distance of 335 picometer, and here carbon carbon distance is 154 picometer. In case of boron nitrate, the layers are separated by a little shorter distance of 330 picometer, and here boron nitrogen bond distance is 145 picometer. Okay. So, this is how the boron nitrate layer structure looks like. Okay. So, the hexagonal B3N3 motif in this layered form of boron nitrate appears in a group of compounds called borosines. They are also known as borosines. Essentially, a borosine molecule is isoelectronic with benzene. Borosine is a colorless liquid. I have shown here, melting point is 215 Kelvin and boiling point is 328 Kelvin, with an aromatic odor, and physical properties are essentially similar to those of benzene. And in fact, borosine was first prepared by Alfred Stock in 1926 by reacting B2H6 with excess of ammonia heated to a temperature of 250 to 300 degree centigrade. You can see that equation is shown here. 3B2H6 plus 6NH3 gives B3H6N3 plus 12H2. And one can also prepare using other methods. For example, BCl3, when it is treated with ammonium chloride at 693 degree centigrade using chlorobenzene as a solvent, If you take this boron nitrate and treat this one with sodium borohydride, it gives back borosine along with B2H6 plus 6 equivalents of NaCl. Okay. So, the BN distances in the planar BN ring are essentially equal, all are equal, and that is 144 picometer. The delocalization of the lone pair electrons of nitrogen to vacant p orbital of boron is responsible for making this BN bonds are equal. That means, you have delocalization very similar to that we see in benzene, okay, and because nitrogen has a lone pair and boron has a empty orbital. So, there is a delocalization of these electrons. Borosine is known as inorganic benzene because of its similarity in structure and physical properties to benzene. Okay. So, this is how one can write the borosine structure here. Of course, one can write alternate structure and also one can write a resonance structure. These kind of interactions with nitrogen lone pairs with empty p orbitals of boron responsible for multiple bond character here. Okay. And of course, here some bond parameters I have given here. Okay. And this is the analogous trichloro compound. So, the boron hydrogen bonds are replaced by boron Cl bonds here. Okay. So, let us look into some reactions of borosine. So, when it is treated with water, it forms BH, OH, NH2, which in turn gives hydroxyborosine, and if you treat with little excess of water, it gives boric acid. On treatment with hydrochloric acid, it forms chloroborosine. Okay. Of course, the reaction of boron trichloride with ammonium chloride can also give this compound, and this one on treatment with methyl magnesium bromide can give you the corresponding methyl derivative, that is Me3 B3 N3H3. Okay. This is planar structure, whereas this one do not have a planar structure. This has a cyclohexane type structure. So, something like this. Something like this structure is there. Of course, they are having so it continues like this, and of course, N has H. It continues like that. Okay. So, let me look into the uses of group 13 elements and their compounds. Very useful sodium borohydride can be prepared from boron trimethoxy derivative. On treatment with sodium hydride, it gives sodium borohydride, and titanosin dichloride on treatment with boron hydrate, sodium borohydrate, gives this compound, and in the presence of metal catalysts, sodium borohydrate releases hydrogen. Exploiting this reactivity, sodium borohydrate is used in prototypes of direct borohydrate fuel cell. So, the hydrogen is generated for fuel cell by catalytic decomposition of the aqueous boron hydrate solution that I have shown here. So, essentially NaBH4 plus 2H2O gives NaBO2 plus 4H2 comes out. Okay. So, this is what we use, that means you can just store it as and when it is required. One can react with water to generate H2. Okay. And so, that means one can think of using it as a hydrogen source in direct borohydrate fuel cells. Okay. So, boron is extremely hard refractory low density solid of very high melting point and very low electrical conductivity, that is important. And boron fibers are used in making bulletproof vest and light composite material in aircraft, and 10 boron isotope has high ability to capture neutrons. So, metal borates are used in nuclear applications as protective shields and control rods. Essentially boron metal borates having 10 boron isotope. So, borax and boric acid in making heat resistant glasses, that is Pyrex glass, and also borosilicate glasses, and also they are used in glass wool and fiberglass manufacturing. Borax as a flux in soldering metals, medicinal soaps, orthoboric acid as a mild antiseptic are some of the uses. Okay. And aluminum is a very bright silvery white metal with very high tensile strength. So, as a result it possesses very high electrical and thermal conductivity. In fact, electrical conductivity of aluminum is twice that of copper by weight to weight basis. Because of this one, and also it is light metal. So, one can make conveniently alloy with copper, manganese, magnesium, silicon and tin, and also aluminum can be made into thin wires, plates, foils, sheets used in packing, utensil making, construction and also in aircraft engineering. Two important compounds of group 13 elements in organic synthesis are essentially aluminum hydride and lithium aluminum hydride. So, one can prepare these things conveniently starting from aluminum chloride and lithium hydride. For example, lithium hydride on treatment with aluminum trichloride gives very useful lithium aluminum hydride. Okay. And if you use excess of lithium aluminum hydride, one can get aluminum hydride as well. One can also prepare by directly reacting lithium with aluminum in presence of hydrogen gas to prepare lithium aluminum hydride, but this requires very high temperature. Okay. And of course, the usefulness of lithium aluminum hydride can be seen in the following few reactions. Okay. Or one can also treat this one with or with dimethyl zinc, so these are the some of the applications of lithium aluminum hydride. Okay. And B2O3 finds important application in glass industry. The glass industry in Western Europe and US account for about half the B2O3 consumed. Okay. And fused B2O3 dissolves metal oxides to give metal borates. Fusion with the sodium oxide and potassium oxide results in viscous molten phase, rapid cooling of which produces glass. Fusion with appropriate metal oxides leads to colored metal borate glasses, and borosilicate glass is of particular commercial importance. It is formed by fusing B2O3 with silica. Borosilicate glasses include Pyrex, which is used to manufacture most laboratory glassware as well as kitchenware. It also contains high proportion of silica and exhibits a low linear coefficient of expansion. As a result, it can tolerate very high temperature, and on cooling rapidly it does not break. The refractive index of Pyrex is 1.47. The Pyrex glass is 1.47, and if a piece of clean Pyrex glassware is immersed in a mixture of methanol and benzene in 16/84 weight, okay, it seems to disappear. Okay. This gives a quick way of testing if a piece of glassware is made from Pyrex or not. You should remember that one. The refractive index of Pyrex is 1.47, and if you take a mixture of methanol and benzene in 16/84 weight, okay, its refractive index also will be 1.47. As a result, what happens in a container made up of Pyrex, if you start adding, what happens? It appears like glassware is disappearing or dissolving, and sometimes people use this in magic tricks also. That is an indication of checking whether the glass we are using is Pyrex or not. Fiberglass falls into two categories. One is textile fibers and insulation fiberglass. Of the textile fibers, alumina borosilicate glass has most widespread application. The fibers possess very high tensile strength and low thermal expansion and are used in reinforced plastic. Insulation fiberglass includes glass wool, which contains about 55 to 60% of silica and 3% aluminum oxide and 10 to 14% of sodium oxide and 3 to 6% of boron oxide, plus other components such as calcium oxide, magnesium oxide and zirconium oxide. Okay. And also this boron nitrate finds application in aerospace industry, and also it is an excellent thermal insulator, and also it is used in cosmetics and also personal care industries. Okay. And in fact, hexagonal boron nitrate was first developed to meet the needs of the aerospace industry. It is stable in oxygen and is not attacked by steam below 900 degrees centigrade. This hexagonal boron nitrate I am talking about. It is a good thermal insulator and has low thermal expansion and is resistant to thermal shock. So, these applications have led to its use in industry to make high temperature crucibles. Boron nitrate nanotubes have been formed by depositing boron and nitrogen on a tungsten surface under high vacuum. These nanotubes could be suitable for high temperature conditions under which carbon nanotubes would burn. Okay. The softness and sheen of powdered boron nitrate has led to its widest application in the cosmetics and personal care industries. It is a non-toxic and presents no known hazard and is added to many products up to around 10%. It adds a pearlescent sheen to products such as nail polish and lipsticks, and is added to foundations to hide wrinkles. Its light reflective properties scatter the light, making wrinkle less noticeable. Okay. So, aluminum alloys also find lot of application. It is light, has high electrical and thermal conductivity, high reflectance, and is easily machined. So, alloy strength is achieved by using aluminum. So, the greatest use of aluminum alloys worldwide is in building and construction. For example, aluminum, copper, magnesium alloy is used in aircraft. Aluminum and copper alloy is used in satellites and space vehicles. Aluminum alloys in car is increasingly prevalent, and they are used to make body panels, engine blocks, wheels, bumpers, radiators and trims. Aluminum alloys are also used to make cooking utensils, refrigerator bodies, air conditioning units, toys, tools and collapsible toothpaste and cosmetic tubes. The chemical and physical properties of aluminum makes it the most widely used non-ferrous metal. It is light, has high electrical and thermal conductivity, high reflectance, and is easily machined. These products are enhanced by the impervious oxide layer on the surface, which makes it resistant to corrosion. That means self protection through the formation of a layer, that is called passivation, that also gives extra resistance towards corrosion. So, I will stop at this stage, and in my next lecture I would introduce Wade's rule to explain boron hydrates, and then look into some problems based on group 13 elements. So, thank you very much. Have a very pleasant reading of inorganic chemistry. See you in my next lecture.